We move to our next presentation, titled Unique Challenges in Load Rating and Retrofitting a 1920 Chicago Building for Repurposing as a Data Center. And our speaker for this webinar presentation are Kevin Walsh and Ahmad Alshwaiki. Kevin Walsh, he is a principal at Frost Engineering and Consulting in Mishawaka, Indiana. He is a registered PE or SE in 24 states. He completed his PhD in civil engineering from the University of Auckland in New Zealand. Dr. Walsh is on subcommittees of ASCE and ACMA standards. He is concurrently a faculty member at the University of Notre Dame, where he leads research projects on FRP, historical building elevations, evaluations, and other topics. Welcome, Kevin. At the same time, I would also like to introduce our co-speaker for this presentation is Ahmad Alshwaiki. Ahmad is a business development manager for FYFE. He helps structural engineers use externally bonded FRP systems for structural strengthening of their buildings. He has over 6 years of experience in the composite strengthening industry and has a mechanical engineering degree from Oklahoma State University. I extend warm welcome to you both.
Okay, wonderful. Yeah, so I'm going to talk a little bit about a building that we analyzed and retrofitted, and it's a fairly prototypical building for 1920s Chicago, and I'll explain, I guess, why we suspect that later. There was a very unique aspect of this project related to the foundation design, but given the scope of this virtual seminar, I'm going to focus very much on what led us into the FRP retrofitting of the columns, and happy to answer questions about the other parts of the project. I'm going to do the introduction, and then I'll hand over to my colleague Ahmad. Typical disclaimer here, you guys have probably seen that a few times today, so we'll move on. Aparna, thank you for the introduction. She did mention that in addition to being a principal of a design firm, I'm also a faculty member at the University of Notre Dame. And a little plug here, I was really excited. I'm very excited to see more articles regarding adaptive reuse projects being published in structural engineering journals, such as this iStruct one, which came out earlier this year. At the University of Notre Dame, we have started up a historic preservation master's, which is hosted in our School of Architecture, which is quite appropriate. But we are going to be cross-listing a lot of classes between engineering and architecture, and we're really excited to get more professionals into the space, especially young professionals. So anybody who's involved in academic, the academy or pedagogy, who's looking to build this topic in classes relevant to it at their universities, please reach out to me. I'd love to compare notes with you. So I'll talk a little bit about our existing building today. And some of you may recognize it, although I'm not at liberty to name the address of the location in this particular venue. But it's located in the Loop, for those of you who aren't from the area, that Chicago's downtown. It was built in 1923 as a manufacturing facility. It's 10 stories above grade, plus a penthouse, plus a basement level. And I'll talk about why that type of construction is quite textbook, literally, in a few slides from now. We have circular reinforced concrete columns and flat slabs with drop slab panels to limit the propensity of punching through with the columns. It's a little bit difficult to see in this picture because it's painted black, but you'll see it more clearly on future pictures. The slab is typically 9 inches thick with diagonal reinforcement. It was renovated in 1998 and turned into a carrier hotel. Nowadays, with data centers, we would refer to this as a co-location center. So it is being repurposed as a co-location center. It was a fairly robust building, but we are adding quite a bit of loads into it. For anybody who's in the data center industry, you know our loads can be quite high. You'll see the typical bay dimensions are about 20 feet by 20 feet, just a little short. Our typical floor height's 11'2", but interestingly, the top floor is a bit taller, and that did become an issue of concern later on in this project when we added a bunch of load to the roof. So I'll talk about the existing concrete strength. I've done a lot of retrofits, and I've worked with a lot of people who've done historical evaluations and retrofits. And typically we find the values in, say, ASCE 41 to be fairly good and often conservative. So just as sort of a baseline here, if you look at the slabs and columns for this particular era of building, we're expecting about 2 to 3 KSI concrete for the slabs and about 2 to 4 KSI for the columns. Now, I've always been a big proponent of in situ material testing in every bit of work I've done for a few reasons. One, you typically find that your materials are a lot stronger than you think, especially in well-built, what appear to be well-built buildings such as this one, and it is a well-built building. And also there is a slight chance of having the other sided error where maybe the material isn't quite as good as you were hoping for. But, and I know it's, for those of us who work in the space, it's a tough case to make to contractors and owners. You make a bit of a mess, it's an extra expense, you hold up things, blah, 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 but it's incredibly important. And honestly, it is a bit of a plea here. I think our industry needs to do a better job of pushing for more in situ material testing in general. The STM standard for taking cores and testing them more or less requires a 4-inch diameter core. Now, I've talked to colleagues in the industry who, like me, are trying to get away from this because a 4-inch diameter core is very difficult to take, especially when you're trying to get a 2-to-1 ratio of diameter to length. It's a big core, and it's difficult to get, especially when you have tightly spaced reinforcement. Well, here are the cores. And I mentioned before that we do a lot of in situ material testing, but I'm not here to tell you that everything always goes right on every project with which I'm involved with. This one, we did have a challenge that we faced. So we follow the relevant standards. You can see those in the top right-hand corner. We took 2-inch cores from the columns. Why? Well, because the ties were spaced at 2 inches. Yeah, you can go through them with a core, but then you start breaking apart the core, or best case scenario, you've got pieces of rebar in your core, and I always wonder how those affect the test samples, so it's not ideal. So we just took 2 inches there. The average strength of those tested samples in the lab was 2,300 PSI. That's about what we were expecting, maybe a bit low. But when you put in all the adjustment factors, the equivalent F prime C was only 850 PSI. And unfortunately, no, there is not another digit missing there. Hence the exclamation points in the parentheses behind it. From the slab, we were able to take 4-inch cores, average strength 2,000 PSI. Again, pretty solidly in the range of what we're looking for, maybe just a bit low. But again, you follow the relevant standards to come up with your equivalent F prime C, and you're down at 820 PSI. Now, from a structural engineering consulting standpoint, this is a disaster, right? And again, this was unique. Very rarely if I run into a problem where our equivalent F prime C is so scary low, especially as we're about to add a bunch of load to the top of the building, which I'll explain in a few slides. So why did this happen? You go out and look at the condition of this building. There's been no water penetration. It was a very well-built building. I don't trust the results, and I don't think that anybody in particular along the way did anything wrong, either the team that we hired to extract the cores or the lab we hired to do the testing. The reason that there's such a difference between the average strength and the equivalent F prime C is high variability. What could have caused that? Well, micro cracking, and you're going to get micro cracking anytime you take a core. Why was it especially damaging here? These samples were very sandy. I kind of get the sense that there's a lot of compacted sand that didn't necessarily, get mixed in maybe as well as it should have with the cement. But in a structure where you're not necessarily worried about having a lot of cracked concrete from, say, high seismic demands, which isn't necessarily the case in Chicago, it's so long as the structure is intact, having a little bit of uncemented sand isn't the end of the world. There's also a lot of round smooth aggregate, which again, and I've worked in areas of high seismicity, is a big problem once you start cracking the concrete. But again, if the concrete's in good shape and your load cases don't, you expect to keep the building mostly elastic, it's again, not a huge problem. So while there were some unique things about the material mix here, I don't really believe these equivalent F prime Cs are appropriate. And so we went out and, one more point to make about drilled cores. We do expect drilled cores to always be weaker than cast cylinders by at least a little bit. And there's some research out there that proves that. And here's a particular example. So we went to get a third opinion, right? At the moment, we've got the ASCE 41 numbers. We've done our core samples. They're quite disparate. What's the truth? So we spent the extra money on our time because we were quite worried about it at this point, and went out and used a probe, a Windsor probe. Now, what you see here are the averages. I'm not showing you sort of the computation of the F prime C, but we're getting much higher average strength. In fact, this particular Windsor probe that we used had a hard time getting into concrete that was stronger than F5 KSI, and it bounced back a few times. So the results of the Windsor probe are very positive. So now we've got basically 3 opinions on this matter. And what we settled on was we were going to move forward with the project using an equivalent column strength of 1,700 PSI and an equivalent concrete strength for the slab of 2,000 PSI. And why? Well, those numbers are reasonably low. We don't want to go as high as our average results for the Windsor probe. We don't even necessarily want to go as high as ASCE 41 values may permit us, but we also can't be working in the 800 PSI range. Finally, we're working a little ahead. We were fortunate to be tied into the contractor and to FYFE early in this project, We were in regular communication with them, and we knew what was achievable with an FRP retrofit of the columns. So we're cheating a little bit here and looking ahead in the textbook to see how the story ends. And as a result, we were able to settle on low enough numbers that we could justify them based on our range of testing and resources, but also not high enough that we were being non-conservative. So the next thing we needed to investigate was the flat slab reinforcing, and we of course did not have any as-built for this building. There were a few architectural floor plans that we were able to dig up, but nothing structural. So we went out there with a GPR rebar scanner, hired another team to do that. And of course, we expected the rebar, they expected the rebar to be on a grid, and found that wasn't the case. And when they start mapping it out there, you can see the images from the actual building. What you find is there's quite a bit of diagonal reinforcement spanning from column to column, but diagonally from corner to corner. And it turns out that's not particularly unique for this part of the country. So on our bookshelf, we've got a 1918 Concrete Engineer's Handbook by Houle and Johnson. And sure enough, you open it up and there's a picture of almost exactly what we have out here in this building of interest. You can see that they called it a four-way system. And they also refer to their preference of using a drop slab to try to prevent punching shear around the columns, which is exactly what we have in this building. If you look in the bottom left-hand corner here, the authors even point out that this is a particularly common type of construction for this sort of interwar era in the Chicago area. And we would expect a few hundred buildings in the area to have similar detailing. Flip through some pages, you see, why do they have this type of construction in the first place? They list a bunch of different advantages based on the construction approaches of the time. But what I thought was really interesting was this figure 40 on the right page. You can see they use a graphic to make a case that when you use this flat slab system, you can get 10 stories in the exact same height as you can get 9 stories with sort of a traditional beam and girder construction system. And our building, in this case, was exactly 10 stories. So literally a textbook building. Now, I do like working on unique projects, but it's also fun to work on prototypical projects because things you learn from them can be applied to a much larger portfolio of buildings, which is always exciting. By the way, we did have a good chuckle with the remarks down here. They experimentally tested slabs and buildings like this, which I love. As Einstein is fond of saying, God has no need for calculus, he integrates empirically. I always trust experimental validation over any type of analysis. But we do have means of analyzing a flat floor slab here. We even did a few years after this building construction book was published. Note in their very last sentence, they say there's really no theoretical method of analysis. The yield line analysis method was developed, I believe, just a few years after this. So a lot was going on in the field of structural engineering design and analysis in the early part of the 20th century. They even have load tables based on their experimental validation. Now, I did not put a red box around anything in particular here. You can see my colleagues sort of hand circle notes. Our geometry and detailing did not match up perfectly with any line in this book. But again, we kind of used it as secondary validation for what we found from our own novel modeling. And we created the NETABS model of the floor system. We laid out the specific equipment locations from the owner, did a comparison, looked at punching shear around the critical perimeter of the drop slabs, and we made sure our deflections were all well within the ACI 318 limits. So now we'll come to the issue of why we had retrofitting on this building, because unfortunately for our friends on FYFE, we determined we didn't need it at all for the slab, although they would have been very happy to have helped us reinforce the slab if needed. But let's talk about the column demands and capacities. This building is being converted into a modern co-location data center, and given that it's in the loop, there's not a lot of ground around the building in order to put sort of the heavy backup generator equipment and server coolers and that type of thing. So they needed to build this new rooftop dunnage, and they ended up adding about 350 kips of weight up to the roof. Here's some photographs I've taken where you can kind of see what it looks like, along with some of the utilities that are up there, and a great view of downtown Chicago from the top of this building. For any of those of you who have worked with building evaluation before, the Chicago Rehabilitation Code basically adopts the language of the IEBC and says that if you only increase your gravity loads by 5%, and moving to the next slide, and you don't increase your demand capacity ratios to lateral loads by more than 10%, then generally speaking, you're quite cool. Now, we always joke in this office, well, how many engineers over the past few decades have already utilized these 5% and 10% allowances, but they do provide us with a bit of a baseline to check the building with. So here's a sort of cross section of our Revit model of the building. You've got the rooftop dunnage up on the top. Again, we're adding about 350 kips of additional weight up there that has not been there before. We did discuss potentially saving a little bit of weight by removing the brick penthouse, but it ended up not being necessary, fortunately. And then that gave the owner more flexibility with what they wanted to do with it. What you can see is the increased axial vertical demand on the worst case column on each floor going down the building. So obviously your columns that are most local to where the new load is, those are the columns sitting on top of the 10th floor supporting the roof. The column that's carrying the most load based on being smack dab in the middle of the center of weight of this new rooftop dunnage has an increased load of 182%. And as you go down the building, you dissipate that load quite a bit. So then, we're required to carry out analysis and see if the columns are overloaded from a design to capacity ratio standpoint using modern building standards. So at this point, we're using the relevant version of ACI 318 as is required by the Chicago Rehab Code. And the columns were remarkably strong. Maybe with reducing a little bit of weight from the rooftop dunnage, we may have even been able to get away without retrofitting them at all. But the good news is the retrofit provided such a high improvement in performance and really was such a small portion of the overall construction cost for this project. The owner was very happy to do it, which was great, and it certainly made us feel a lot better. We ended up wrapping critical columns on the top 2 floors of the buildings. Now, one unique thing about these columns, the spiral pitch on the ties is quite good. It was only a 2-inch pitch, and for those of you who are structural engineers, then that regardless of what our unconfined concrete strength is, we're going to get pretty decent performance in terms of strength and strain capacity for the confined concrete core. The issue is that we have a very large clear cover. It's about 3.5 to 4 inches on either side. That's more typical of sort of outdoor concrete that's exposed to wet soil, a bit odd by modern standards anyway for interior concrete columns. The issue here is that over half the cross section of the concrete columns is actually unconfined. And as a result, we were getting some pretty high, undesirably high demand capacity ratios with our new rooftop dunnage, largely governed by the LRFD load combo that you see below. Now, for those of you who maybe are from the West Coast, you might be surprised. Oh man, you're controlling LRFD load combo included earthquake demands. Well, arguably there's not strong wind load on this building in one direction. It is in a contiguous block of buildings in Chicago. You might get some substantial wind load in the other direction, but it's an extremely heavy building. Remember, we've got 9-inch thick slabs up the height of this thing. Concrete columns, mushroom tops on them, drop slabs. It's a very heavy building. And the controlling effect on these columns was a compounded axial demand. So we already have downward forces from the extra weight that we're putting at the top of the building on the rooftop dunnage. And then we have additional compressive forces in the columns from the overturning effects of the earthquake demands. Shear is not a huge issue. These columns are slender enough, and again, they have nicely tight spiral reinforcing. So it's really the compressive stresses that concern us. And of course, those highest compressive stresses are largely happening outside the existing confined area. So we really need to confine the entire cross section of the column, and we're going to be in good shape. And again, that ended up being very quick and relatively inexpensive, thanks to our friends at FYFE. Speaking of those friends, Ahmad is on the call, and I'm going to let him talk about the installation of the FRP wraps.
Awesome. Yeah. Thank you, Kevin. I appreciate everybody having us today. Yeah. I was great working with Dr. Walsh on this project. We're a material manufacturer, and what we looked for in collaboration with the structural engineer of record is for them to tell us really, how much extra capacity, usually tension capacity or positive moment, negative moment. In this case, how much extra confined strength that their concrete columns will get to in order for the structure to work and for the new loads on the roof to dissipate within the structure. So what they were looking for was for us to increase the F sub C from 1700 psi to 5100 psi, which, as you guys can tell, it's about 3 times as much, close to that. So that's a significant increase. What we did is we ran through the ACI 440 equations and calcs, and our engineering team determined that at using a 0.006 strain and using 3 layers of our 0.08 inch thickness material. We were able to design an FRP solution that took the compressive strength of these concrete columns from 1700 psi to 5100 psi. At 3 layers, what we're looking at is about a 1/4 inch thick on these columns. And what we're trying to do is we're orienting them transverse. So just like a steel jacket originally, but with FRP instead, a lightweight externally bonded tension member oriented in the transverse direction. Basically, what'll happen is that you're able to confine the extra strength and the extra strength and the strain in the concrete column when it tries to move and that was the main goal. So we're not doing anything longitudinally on this structure. We were just doing 3 layers on each of the 21 columns in between the 9th and 10th floor. The next slide will have some pictures of those columns or more of the design. Yeah. So again, just the Typho SCH41 2X system. That's our 0.08 inch thick. Each FRP strip is 2 feet wide. So you just start from the bottom or the top. In this case, we started from the top, and you would go down 2 feet at a time. That's the typical width of the FRP strip. It's butted up next to each other, so you're not having to develop anything longitudinally. But when it comes to transverse, we did do an overlap about 12 inches to get that system all put together and get that confinement strengthening that we're looking for. And then here's some pictures from the job site that I took when they were doing the install. These are columns that are contact critical. So because the FRP can wrap on itself, so you can find the element and then you wrap the FRP back on itself. We're not really relying on the bond between the FRP and the substrate to get the strengthening that we're looking for. We're really relying on the FRP bonding to itself. That's why it's contact critical, not bond critical. So the surface prep on these columns wasn't a huge deal. It wasn't very labor intensive like a lot of surface prep for FRP is. Thickened epoxy and priming the concrete column. Any bug holes, fill those with thickened epoxy, and then we were wrapping three layers full length of these columns. On the top left there, you can see an area where the contractor has a saturate bath area where they're basically saturating these FRP strips. The quality control on that is to make sure your FRP strip, you weigh it before you saturate it, and then you weigh it after. And if it's 100% increase in weight, that's 100% saturated. Then you got a couple guys that are going around the columns and fully confining them with 3 layers. Again, each layer is 0.08 inch thick. 0.24 inches thick for the whole system. So you're not really adding a lot of, you're not adding a lot of new concrete column or anything like that. And it's not heavy like a steel jacket. So it's kind of a perfect application for this building that's downtown in a busy area where having a large footprint or working area is kind of difficult. And then in that picture there on the right, you can see them going over the FRP with an acrylic finish right there in the middle. So they're finishing up the concrete as well for it to look really, really good. And you may basically not be able to tell that any FRP was done over there. Yeah, so this is pretty cool. This is something that the FRP jackets and FRP strips can be done with. Is if you have very, very small areas, you can hook the FRP strip or you can just pass it through. You don't really need that much area. That's probably less than 2 inches that they had to demo there from the side of the column. But regardless, we need access to 360 degrees around the column to wrap it around itself. And we were able to do that on this one as well and finish it with that white color as well for a very nice final look. You're not able to really pass your own hands down back there, but when you have an experienced crew that's working, they can get it done, and we can make sure that it's finished with the color that's approved by the owner. And the whole thing was done pretty, like Kevin was saying earlier, it wasn't too costly, and it was pretty time effective. So the client and the owner was pretty happy about this solution. And I think that's it.
Thank you very much.
Great. Thank you, Dr. Walsh and Ahmad Alshwaiki, for your presentation. We do have a question. I'll read it out. The focus of your column retrofit appears to be focused on strength. However, with this increased dead load from dunnage, creep and modulus issues, including differential settlement, are likely more critical concerns. FRP wrapping has no effect on the modulus or on the creep behavior. I do agree that the strain capacity is improved, but not the path to that strain. Can the speaker comment on this?
Yeah, so that's a wonderful point. What I will say is it's by increasing the equivalent strength. Obviously, we address the load. Now, that I agree, that doesn't directly address the creep. It is 100-year-old concrete. So while it's still subject to creep, it's not going to be as sensitive as brand new concrete is to creep. Now, the other point I'll make is the 350 kips load is quite high. It's not insignificant. And you can see that we are increasing, our worst case column on the 10th floor, by an extra 82% of load. And that's not significant. But a lot of this dunnage structure was concentrated over a few columns. So it's not like it's necessarily occurring on multiple columns. And this is a very, very stiff building. Now, we didn't do a progressive collapse analysis where if you remove one column, you see how it behaves on the rest. And, maybe if we're in a region of higher seismicity or we had a bigger, sort of attack concerns, we might have. But, a rigid diaphragm system like this, in my opinion, is going to do a pretty good job of redistributing loads if you do get a little bit of creep deformation on one of these columns. So I don't mean to be flippant about it and say, oh, it's not a big deal. It's a great question. I'll admit it's not something we look closely at, but I guess I'm explaining why we didn't put a lot of thought into it.
Mm-hmm. Okay, yeah, thank you. Moving forward with the next question, we have, why was a saturating machine not used to impregnate the fabric with the epoxy saturant? It doesn't seem that all the fibers of the fabric would be saturated.
I'm going to let Ahmad handle that one.
Yeah, good. No worries. I got you, Kev. Yeah, good question. Usually a saturator machine is used when there's a high volume of FRP that needs to be saturated in order to get the job done. For this job and with how many columns we were doing, the contractor didn't feel like it was cost effective for them to have the saturator out there. Using the manual saturation system is still an acceptable method to saturating FRP. And there are quality controls, like I had mentioned. If you have an FRP strip and you're manually saturating it, you just need to make sure that it's doubled in weight, plus minus 5%, and it can be saturated manually on site. So I would have to ask the contractor exactly why, but it all comes down to money. And I bet you that they ran the numbers and they found that it just makes more cost effective for them to do it manually than to do it automatically.
Okay, thank you. We have another question. Considering how critical FRP to the capacity increase, was fireproofing applied? If not, is the structure able to support the design load without FRP during fire?
Maybe Ahmad can answer the first part of that and I can answer the second one.
Yeah, I think, and let me just double check. So I think we used a product called RR, which is it's a class 1 or class A flame and smoke. It's not an hour rated system, but let me double check that before y'all hold me to that. And then Kev, if you want to handle the rest of the question.
Yeah, to be honest, we started with a pretty simple analysis of the columns, and we needed to go quite more detailed from that and use some of the best software for analyzing columns and getting the most capacity out of them that we can. What I will say is I don't have any concerns about if you removed all the FRP and even if you had 350 kips up the top, I don't have any immediate concerns about the building collapsing instantaneously. Our DCRs, despite notwithstanding the high increases in loads, our DCRs were still quite manageable. And keep in mind that these are demand capacity ratios based on modern LRFD standards in ACI 318 and ASCE 7. So they're not sky high. It's not like they're 2 or 3. They're a little bit, they're about 1 and maybe a smooch over 1 in a couple of cases. So no, I don't have any concerns about it. What we find for those of us who work in the data center industry is that over the lifespan of buildings, more and more MEP tends to go in than you designed or retrofitted a building for. And so we tend to be perhaps overly conservative when we're working in this type of building. So if we were, it's a great question, because you always worry about, you know, what happens in the worst case scenario. And if you did lose the FRP in a fire, which for the reasons Ahmad said, I'm not overly worried about, and we have 3 layers, but even in that situation, no, I don't have any concerns about the columns immediately coming down. I would want the building retrofitted before it was occupied and put back into service the way it was before the fire. But no, otherwise it doesn't, we're not cutting it too close.
Great, thank you. Our next question is, the increase in concrete strength from 1700 to 5300 psi seems to violate all strength limits in ACI 440.2R. How was this justified?
Yeah, it's a great question that I don't have a prepared answer for, so I would need to look into that and follow back up with you.
Okay, sure.
I'm sure between me and Ahmad, we can ask their engineering team to respond to that.
Okay.
And what I will say is that we didn't need 5100 really. Obviously, we're asking for more in our performance-based spec requirement than we really need. So even getting less than 5100 would have been acceptable for our design. But why can we say that we're going for 5100 nominally? I will have to get back to you on that, unless Ahmad, you have any insight.
No, I'm right there with you, Kevin. I'd need to ask our folks that are much smarter than me at FYFE to get an answer. So, but I can get an answer on it. Well, no issue.
Yeah, sure.
To explain a little bit about how this relationship worked, I mean, FYFE made it very easy for us. Now we flip through 440 as well, just to familiarize ourselves with it. Our firm does a lot with FRP, but usually other types of FRP. So we don't do a ton of reinforced concrete retrofit with it, although we've had great success from our opinion when we have. But the easy part for us is, we told FYFE's team, who was very competent engineers, what we needed, and we effectively delegated that portion of the design to them. Reviewed their calcs just like we would as EOR for any other type of submittal, but we're very happy with it.
Great. Thank you. We are taking one last question. With the high increase in axial capacity, if FRP fails, the structure would collapse. How did the owner ensure that damage to FRP will occur in the future? Okay.
Maybe you can ask the front part of that question again. They're asking regarding mechanical damage.
With the high increase in the axial capacity, if FRP fails, the structure would collapse. So how did the owner ensure that damage to FRP will occur in the future?
Yeah, I'll defer to my answer before. It's a somewhat similar question to about the fire, where we wanted the FRP to make sure that we had a very high performing facility. Our clients in this center are some of the few owners that are willing to go well above building code, minimum building code requirements, which is why we like working with them so much. I am not concerned about the immediate collapse of this building should the FRP suddenly be removed. So I think there's a misconception here over what we were trying to get out of the FRP. We are not relying on the FRP to hold up the building, but in an ultimate load case where you had the design basis earthquake in Chicago and you had the maximum amount of oil and coolant up on your roof, we would have DCRs around 1.0 and maybe a few percentage points over. And maybe on some projects, that's good enough. On this one, for our clients, it wasn't. So I'm not overly concerned about the imminent collapse. I think I would guess the basis for this question comes from a history of when we've often used FRP to retrofit, say, girders in a parking garage, and we potentially change the governing limit state. We are not changing the governing limit state in this building by putting in the FRP. That is more of a concern when you move something from, say, a ductile flexural limit state into a more brittle type of shear or compressive shear limit state. But we did not change the limit state by use of the FRP on this project.
Great. Thank you so much. Thank you, Kevin. Thank you, Ahmed, for your presentation and for answering all the questions.